In this video, we will talk about the definition of work. And we'll talk about the work done by several common forces. Okay, and in the next video, we'll talk about work done by a special type of force called conservative force. Okay, so those will be for the next video. Now again, this video excuse me, is about the definition and some examples. So what's work? So first, let's think about this problem. Let's say there's an object, okay, and it's on a surface, sitting on a surface. Now we apply a force along this direction to the right, and this object under such a force has a displacement. The displacement is given by this vector. That's the position vector, displacement vector. Okay, I think it's called delta S. Okay, now to specify the effect of force F for this object, we're going to define this quantity called work. Symbol is W, and it's given by force F times delta S, okay, if they're in the same direction. Okay, let me specify this one, what are in the same direction. So F and delta S, they're in the same direction. Now what happens if when a similar situation like this one, if I have a force, let's say acting on, let's say, the same object, okay, and the object again move some displacement along this direction. However, the force is this way. Okay, and the displacement is this way. Now we will also want to specify the effect of such a force on this object's motion. Now there must be some difference, right, in this case, because the previous force F seems to help this object's motion in this way, right, along this direction. But in this case here, the force is actually opposing the object's motion. Okay, so the object must have a velocity along this way. Let's call this VI. Okay, and that's also the velocity direction. Okay, now in one case the force is in the same direction as motion direction, the other case opposite to the motion direction. So there must be some difference in defining the effect of force F, and that's why we add a negative sign here to represent that this force is not helping this object's motion, is actually opposing this object's motion. And in the future, when we talk about the effect of the work on the object's energy, then we'll see this relation. Okay, but it's for future. Right now, let's say we just write this down. So F and delta S in the opposite directions. In the opposite directions. Okay, so we should have a negative sign here to define this difference. Okay, so in fact, there's a very general relation. So let me now draw a picture for the general relation between them. Now let's say still we have an object that is moving along this initial velocities direction, and it has a displacement delta S in the end. Okay, but now the force is not in the same direction as the velocity or in the opposite direction to the velocity. It's actually at some direction that makes an angle, let's say theta, with the displacement. Okay, now how do we specify that? It clearly should have some difference from the previous two cases, right? So how can I define that? So it turns out that I can do a decomposition of this force into two directions. Okay, so one direction here has component F cosine theta, okay, and the other component is F sine theta. Now clearly F sine theta does nothing to this object's motion. The motion is this way, right? So and F cosine theta is useful one, so we say this component is useful and the other component is useless. Useful means that it does work, does some work here, and useless means that there's no work done by this component of the force. Okay, so I'm going to use this cosine theta. All right, so that's F delta S cosine theta to represent the work done by F in this situation. And actually, you will see that this case is like a general case. It can reduce to the previous two special cases. So these are special cases. So let's see how we can do that reduction. Now in the first case, we have theta equals 0 degree. Okay, so the angle theta here is between F and delta S. Between F and delta S, okay, we have angle theta. So now in this case here is 0 degree angle. So that's why when I plug in 0 degree angle here, I get F delta theta. That's the one that we wrote down earlier. Now if in the second case here, the theta here equals 180 degrees. So to plug in this formula, I get -1. Cosine 180 degrees, -1. So that's why we have this negative sign here to represent the effect of force, the work done by the force. Okay. Now to summarize the work definition, so work is defined as the force dot product displacement, right? So, and I also want to make this definition general. So I want to say that there's a infinitesimal displacement, ds. Okay, so now let's say here is the an object's trajectory. I'll move along this initial to final curve. That's the path of this object's motion, and throughout this trajectory, we can pick some location. Okay, at this location, let's say there's a force F. There's a force F. Look like this, and then we also want to divide the path into infinitesimal displacement. I call this delta S, ds. Okay, so ds is along the tangent line, and force F is along some arbitrary direction, and they make some angle at this location theta. Okay, so that's what we define as F dot ds. Okay, it's given by F ds cosine theta. Right, that's some kind of local definition for just this point, and that will be the amount of work, infinitesimal work done by such a force. And since we're interested in the total work done by such a force, so we want to do integral here from initial SI to final S final, the two positions, and that give us the work. Okay, so let's talk about some special cases of the some special force, and we'll talk about the work done by such forces. Okay, so the first one I want to talk about is the normal force. Here's one example. Let's say there's a flat surface, an object is sliding on it by some displacement, delta S. Okay, now let's see what is the normal force. Normal force is the force applied on the object by the surface, and the direction is perpendicular to such a surface. That's the normal force. Okay, so that's why if the object is sliding on the horizontal surface, then the angle here is 90 degrees. There's a 90-degree angle between them, right? So the work done by such a normal force would be dot product between the two, and that's normal force delta S cosine 90 degrees, and that equals 0. And also, by the way, the unit, SI unit for the work is joule. All right, that's one situation. But there are some exceptions. So let me show you one example. Let's say there's an elevator. And there's an object right inside the elevator. The elevator is moving along this direction, and later on it has some displacement. So if I look at the this object in particular, it should have some displacement this way, and the normal force is this way. Okay, now in this case, if I calculate the work done by such a normal force on this object, then I should have a 0-degree angle. So we get this value as the work done by the normal force. Okay, so again, it's not necessarily 0. It actually depends on the object's motion, right? Its motion, its velocity direction, and that together with the force direction determines the work. Now the second special force I want to talk about is the static friction. Fs. Okay, all right, let's see an example. Let's say there's an object, okay, and there's a pushing force applied on it, and there's an Fs to balance that. There are also normal force and gravity. Let's call this Fg. Okay, all these forces are acting on this object. But now let's say this object is at rest. Okay, then that would mean the displacement is 0, right? 0. So that's why whenever we talk about the static friction, the static friction does 0 work. It's always 0. Okay. All right. So let's talk about the another friction, the kinetic friction. Fk. So now let's say this object makes some displacement delta s, okay, along this way, and the velocity of the object is this way. Therefore, the kinetic friction is opposite, so Fk is backward, right? It's this way. So now if I calculate the work done by Fk, let's see what we get. So it's Fk dot product delta S, and then that equals Fk delta S, and then cosine 180 degree, right? So now the angle between them is 180 degree. So that equals -1, negative Fk times delta S. So it turns out to be a negative work. So kinetic friction always does negative work. But again, it's not necessarily so. So let me give you one more example about this positive work by kinetic friction. Let's look at this system where we have we have two objects here, okay? Two objects here. And the let's say we have big M and little m, okay? And there's a pushing force, let's say, apply on the big M. So the big M will accelerate, right? Will accelerate and then experience friction, kinetic friction from the ground. And that is not the friction I want to talk about. I want to talk about the friction between little m and big M. Okay, so let's say we apply such a force so large that the little m here cannot keep up with the big M. So little m with respect to the big M here is falling behind, is sliding to the left side, okay, on the surface of big M. So sliding behind means that the friction force acting on little m is forward. So that's a Fk, right, acting on this little m. Now with respect to little m, bigger M is accelerating to the right, okay? So there's a reaction to this friction force. There's this Fk here. Let's call this Fk prime. Again, Fk and Fk prime, the action and reaction according to Newton's third law. Newton's third law, they're equal in magnitude, right? So Fk equals negative Fk prime. So they're equal but in opposite directions. Okay. Now, of course, as I said, that in the from the ground level, from the ground surface, there's also an Fk. Okay. So let me call this Fkg. That's from the ground, acting on big M. But again, we're not interested in this one. We're interested in this one, the Fk acting on the little m. Now, suppose that the little m here, in this case, has a displacement delta S, right, in this way. Then when I calculate the work done by Fk on little m, I would do Fk dot product delta S, and it's given by Fk times delta X, which is positive. Okay, so in this case, we have a positive work. So again, just like before, for the normal force, its work is not always zero. Okay, depending on the motion that we're looking at. So in some special cases, normal force can do non-zero work, and in this case here, the kinetic friction can do positive work, right? Because it's responsible for speeding up the little m. Okay, but in terms of the negative work, we can say the same reaction of this friction force acting on the excuse me, big M, right, is doing negative work. Okay, so now let's continue this discussion here. So now let's say I want to look at previous motion here, the object sliding to the right, and there's a Fk acting on it. Now let's say this object, now after it reaches the rightmost position, then it slides back with some velocity v', okay, going back. And we don't care about what causes this. It could be because some other force is acting to the left side in that direction, okay? And then it will slow down the object first, and then later on at this point turn around, and then the object will accelerate to the left, right, due to that pushing force, okay? Now in this case, we're going to talk about these objects displacement this way. That's delta S, okay? This delta S has the same magnitude as the previous delta S, but in opposite directions. Now in this case, when the object slides back, the friction force is to the right. Now it will change direction, according to the relative velocity direction, right? The kinetic friction can change its direction. So now in this case, when I calculate the work done by Fk, I will do similar dot product, and then there's again a 180-degree angle. Okay, so we get negative Fk delta S. So again, it's a negative work. So you can see that no matter what direction the object is moving, in this case here, the kinetic friction is always doing negative work. Okay, so if I calculate, let's say this process 1, process 2, the object go to the right and then return to the same position, the total work is negative 2 Fk delta S, which is always negative. Okay, and we'll see in the future that this means that the work done by this kinetic friction always dissipate the energy. Dissipates mechanical energy of the system. Okay, and that's also the result that defines this work as non-conservative work. Okay, the force is non-conservative force, and that will be the subject for the next video. Thanks for watching.